Hello everyone, in this video we're going to look at the lesson 8, and after the lesson 8 I will look at the homework as well at the same time, and the same video, maybe another video. Okay, so what do we need to do? Okay, in this one, sampling distribution of x squared. So previously we looked at a sampling distribution of x bar, which is the if it's a normal distribution, it obeys normal distribution of mu and sigma over square root of n. Okay, so now we'll look at the sigma s squared, which is the variance of the sampling distribution. Alright, so if you look at the variance, and you probably can look at the whole thing, or how to find the variance of the sampling. So there's another distribution I would like to introduce to you, is the chi-square distribution. Theorem 8.4, if s squared is the variance of a random sample size n taken from a normal distribution. So if x is a normal distribution, mu and sigma, okay, so s squared is taken from this sample, and this one has a variance of standard deviation of sigma, variance of sigma square, then the statistics chi-square equals n minus 1 square over sigma square is a chi-square distribution. Okay, this has a chi-square distribution with v equals n minus 1 degree over freedom. Okay. Alright, so in the homework you're going to have problems of finding out the chi-square values. Okay, we're going to look at that as well. The value of the random chi-square are calculated from each sample by the formula. So normally the problem will give you the variance, give you the standard deviation, and plug it in, give you the n, so you can find yourself for chi-square. The probability that a random sample produce a chi-square value greater than some specific value is equal to the area under the curve to the right of this value. So okay, the normal sample produces a chi-square value. You're going to have a chi-square, chi-alpha square. This alpha is also a probability, like the area. You know, area is always the probability, right? Okay, it's like this. Like chi-square is a number, like a z-score. Okay, when you look at the normal distribution, have a z-score, and then the chi-square distribution have chi-square value, or chi-square score is just a name word of it, and then this is the probability. If you remember the normal distribution, it gives you the value to the left, right? The area to the left, but now is the area to the right. Okay, so the probability that a random sample produces a chi-square value greater than some specific value is equal to the area to the curve to the right of this value. It is customary to let chi-square alpha represent the chi-square value above which you can find the area of alpha. This is illustrated by shaded region in this region here. Okay, so the table, you have a table when you do a problem, gives the chi-square values for various values and freedom. So the area alpha is the column headings, the degree of the freedom. You can look at those. We can have several problems to practice later. So first, let's look at example 8.7. A manufacturer of a car batteries guarantees that the batteries will last on average 3 years with a standard deviation of 1 year. It says the normal distribution 1 and 3, and the standard deviation is 1. If 5 of these batteries have a life of 1.9, 2.4, 3.0, 3.5, 4.2. Okay, so we give the sample, a sample selected from population. Now this sample, we can find out the variance, s squared, and also can find the sample mean value, x bar. So now, what's the question is, should be the manufacturer still be convinced that the batteries have a standard deviation of 1 year? So which means, since the population standard deviation is 1, they claim that it's 1. So now, is that the standard deviation remains still 1, like the population? We have to check it again. So we can find the variance of the selected group of data. Select a sample if the variance of the selected sample is too big. For example, you got a selected sample is 5. Well, there's no reason. I believe that the variance of the population is 1 because your sample variance is so big, right? So what you need to do, they have a, maybe you think 1.1 is good. 1.2, okay, I still believe it. 1.3, yes. 1.4, but if you got a 5 or 100, no, it's too far away from 1. So what criteria should I choose to make the statement saying that, oh, I think it's still 1. Okay, so I think this, the standard deviation is 1. So what do we do? The chi-square actually help you to build up that criteria. Assume that battery lifetime follows a normal distribution. So you can find S squared. If you give it 5 values, you can use standard crunch to find the variance of this one. It is actually using the, I think you use the variance, the table, or you use something to find X squared. You can find it yourself. You got a variance, which is 0.815. You can use your, you can use the stack crunch to find the variance. Then we can find out the chi-square, which is n minus 1 s squared over sigma squared. N is 1, 2, 3, 4, 5. You have 5 numbers, so it's 4 times 5 minus 1. I just use the 5 minus 1. S squared is 0.815 divided by 1. This is a sigma square is given. We got 3.26. Well, now I got a chi-square is 3.26. All right. Chi-square is 3.26. I think 0.815 is still very close to 1. So compare 0.815 and 1. They're pretty close. Okay. But I'm not sure if I want to make that statement say, okay, it is still 1. All right. So since this is a sample, you should have some difference. So let's look at the chi-square value. All right. So what do we need to compare? This one is 3.26 is the value from chi-square distribution with 4 degrees of freedom. So the degree of freedom equals 4. 95% of the chi-square value with 4 degree of freedom fall between, okay, so 95% of the chi-square value fall between 11.143 and 0.484. Let's check it out. This one is in this region. Okay. So which means, okay, then it falls into this region, which means that the computed value sigma square for this population is reasonable. Therefore, the manufacturer has no reason to deny or to suspect that the standard deviation is other than 1 year. Although we only have the sample variance is 0.815, but it's still close to 1, right? All right, so that's the, if you take a square root, it's about 0.9. So that's why it's close to 1, that's why. But we have to have a standard to find out why we support it, why we reject it, right? It's pretty much like a hypothesis test we're going to do later. All right, so 8.3, continue. So we have the chi-square degree. Why do we have a degree 1 less the degree of freedom? This degree of freedom as a measure of sample information has explained this. Okay, so there is 1 less degree of freedom, or degree of freedom is lost in the estimation of mu. And then there are n degrees of freedom instead of n is n minus 1. Okay, you can read that section to understand that. 8.6. Let's look at 8.6 is T distribution. T distribution is sometimes when you have a population, you don't know the standard deviation or the variance of the population. You only know the variance of the sample. Since sample is small, right? You know the mean value of the sample is small. Sample means small one, right? Small amount of numbers. You can find the variance of the sample. We don't know the sigma. We don't know what it is, the population sigma. So now another distribution x bar minus mu, but mu is known, the population mu, over s over square root of m. This obeys a T distribution. This obeys to T distribution. Okay. So everything else is the same. Is you change that s, change the population, sigma over square root of m, change the population variance, standard deviation into the sample variance, then it's a T distribution. Okay, so T distribution also give you a probability as well. It's pretty much like the normal distribution, they have their own distribution table. Okay, so this is define of the t-distribution. Normally, we're going to use a t-distribution. We're not going to use this probability density function of, okay, let me find out tv plus 1 over 2. What's that? And then find the gamma of v over 2 over square root of pi v of all of that, all of these things, of square root of v of the negative v plus 1 over 2. We're not going to do that thing. Okay, so instead of doing the, the normal distribution, square root of pi 2 sigma 1 over square root of pi 2 pi sigma e to negative 1 over that. Okay, so we don't manually find out these values. Okay, so what they do, they provide you a table, like a normal distribution table. You just can find the probability from the table. Alright, so what's the t-distribution look like? If you look at t-distribution, the t-distribution is like a bell shape as well. Okay, it has a symmetry property about the zero of t-distribution. It's very much like normal distribution. Okay, but it's a little bit different of the shape, but it's very much like a normal distribution. You can see the shape is bell shape, but the normal distribution is they're very, very similar. Okay, when the degree of freedom goes to infinity, go very big, it's exactly the same as normal distribution. Okay, why? Because the t-distribution will be exactly as normal distribution when the sample size goes to large, infinity. Why? Because the t-distribution is based on what? Based on your sample. If your sample goes very large, just like your population, then for sure it obeys normal distribution like the population, population distribution, right? If n goes big, your sample will be very big, just like your population. So they are exactly the same. That's very reasonable, right? It's going to be the same as the population distribution. Originally, it's normal distribution, right? So if the degree of freedom is big, it's big enough, it's very big, then it's almost the whole thing is all of the population samplings. So then the t-distribution is exactly as the normal distribution. Okay. Alright, so that's one thing you need to know. Another thing we need to know about t-distribution values is t1 minus alpha equals negative t2 alpha. Okay, I think in the z-score you also have pretty much the same thing. Okay, because if you check out a z negative 0.55, then this one equals 1 minus z 0.55. You know that, right? Yeah. Okay, so t1 minus 1 half 1 alpha equals negative t alpha. Okay, this is also negative. Okay, for example, if you're looking at t 0.95, this equals negative t 0.05. Okay, the example 8.8 8.9 have this example. Look at the examples, and then there's the example 8.11 I would like to explain. So a chemical engineer claims that population mean yields of certain batch process of 500 gram per millimeters of raw material. To check this claim, he samples 25 batches each month. So n equals 25. If the computed t-value falls between negative t 0.05, t 0.05, he is satisfied with this claim. So what conclusion should he draw from a sample that has a mean of? So the population claim says x mu equals 500. So now what he got is a sample mean value is 518. It is very close to 500, but we don't know yet. We don't know whether it's really whether we need to support or not. So we have to find out the t-value. Okay, so t-score equals x bar minus mu over s over square root of m. So what I find the t-value here, so it's 518 minus 500. The variance of the sampling is given is 40 over square root of 25. So I find the t-value is 2.25. Now I want to know if this 2.25 falls into this area. If it's pretty much like a normal distribution. this is 500. Okay, this is if anything in this area, for example, this is a t.05, this is negative t.05. Anything in this region you think, well, this is close enough to 500. Anything to this place or this place is too far away from 100. That's what it means. So let's check if the 2.25 fall into these two values. So first I find the negative t.05. You find the value, which is 1.711. The probability that t-value is equal to greater than 2.25 is approximately, okay, let me see. From the table, you find t.05 is 1.711 for 24 degrees. Therefore, the engineer can be satisfied with the claim if the value is negative 1.711. So now, what do I got? I got 2.25, which is out of the range. 2.25 is not in this range. So 2.25 is bigger than 1.711. Well, this means the t-value is the probability bigger than equal to the probability of obtaining t-value with v equal 24 equal or greater than 2.25 is approximately 0.02. If mu is bigger than 500, the value of t computed from the sample is more reasonable. Therefore, the engineer is likely to conclude that the process produced a better product than he thought. Okay, so now he got 518 x bar, which is bigger than 500, right? You can get that. And t-value, find out this area, find out this t-value, and all of this together is 95%. Oh wait, is 99%, right? Is if you add those two, is 99. All right. So, and the equal or greater than. So this area, add these two together, the probability is bigger than that is 0.02. Okay. If the mu is bigger than 500, now it's bigger than 500. From sample is more reasonable, so that he can say, okay, that the process is, because this is out of the range, it's not in the range, so we can see that it's bigger than that. Okay, if it's falling into this place, falling into this one, for example, if you got 1.5, t equals 1.5 from here I got t equals 1.5, this in this range, so you're going to say, okay, not much difference from 500. Now I got t equals 2.25 is way bigger than the up boundary here, so the conclusion is it produces a better result, better product. Okay, so next page we're going to look at the F distribution. F distribution is U over V1 over V over V2. So what is F distribution? F distribution, you can think about F distribution is the sample variance of S1 square over S2 square. Two samples variance. Okay. Now U and V be two independent random variables having chi-square distribution with V1 and V2 degree of freedom respectively. Then the distribution of random F distribution given by density function. We're not going to use this density function find the F distribution value like the T distribution, like the normal distribution. We will have that as a table. We don't give you don't need to take the integer from 0 to 1, all of this HF so big long function. Okay, you're going to have a distribution table, probability distribution table. So the F values is given as is very much like a chi-square. You know, the chi-square distribution is pretty much like right? This. So the chi-square and chi-square 1, the ratio of two chi-square distribution is pretty much have the same like the chi-square distribution. Though this is the F distribution shape. There is another formula. We don't have to prove it. Use F1 minus alpha V1 V2 equals 1 over F alpha V2 V1. So when you look at the table later, when you have the homework and look at table, you're going to have you can find out the table F 0.95, 10, 6. This is the degree of freedom of two samples, equals 1 over 0.05, 6, and 10. Okay, so F distribution is with two sample variance. Normally we're going to compare what's the F distribution do. We can look at the data. Okay, so the F distribution, we can compute the F values, the F distribution values. If S1, S2 are the variance, S1 square, S2 square of two independent random samples N1 and N2, we are going to see if there is a major difference between these two sample variants. Okay, basically want to know if there is a difference between the variance of these two. For example, you want to compare two stock, right? Two stocks. You want to buy the stocks, and you want to buy some to invest, to make investment. Okay, you have some money you want to invest. You buy A or you buy B. So one of the things we want to know is the variance. We want to know the risk. The risk of buying A, the risk of buying B. So they probably either give you high risk, high return, lower risk, lower return, like that. But right now you have A and B as an option. You want to buy either stock A or B. So now you want to know if this A or B, which one, if they have a different, if they have any difference between, if have there any difference in the with respect to the risk, regarding the risk. So what do we compare? We compare the variance, right? We compare the variance of the change. And if the variance is big, like varied too much, the other one the variance is small, then you can tell they have big difference. The variance, the variance of these two stocks are pretty much different. So how to compare them? You just make a ratio. If you divide them, it's bigger than 1. Well, they are different, right? So they have, but well, it's not exactly 1 or 1.5. Then you have some values. Then in this case, you're going to use the F distribution. That's what we do. Okay. So let's look at this one. What is F distribution used for? I just give you another example. Now we look at the what the book says. We answer this question part beginning of this section. The F distribution is in use two sample situation to draw inference about population variance. This involves application of theorem 8.8. However, the F distribution can also apply to many other types of problems involving sample variance. F distribution is called the variance ratio distribution. You see that? Variance ratio distribution. Okay. You want to compare if there is a big difference between the variance of these two distributions. So case study 8.2. In two paints, A and B were compared with regard to mean dry time. The normal distribution applied nicely to sigma A and sigma B are known. However, suppose there are three types of paints to compare. Say A, B, C, we wish to determine if the population means are equivalent. Suppose that important summary information from the experiment is given below. So they give you the sample mean value, give you the sample variance, give you the sample size. The problem center around give you all of these values. It appears evident that data came from distribution with the difference population means. We can tell that there is a difference between the sample means. Okay, although there is some overlap between the samples. Analysis that involves all of the data would attempt to determine if the variability variance between the sample average and the variability within a sample can occur jointly if in fact the population have a common mean. Okay, so is variability between the samples or the variability in between the samples. Okay, so that's what we're going to check, the variability comparison of two variants. 8.8 is the quantile and probability plots. Okay, it's Q quantile and probability plots. In chapter 1, we introduced the experimental distributions. Okay, the motivation of this one is make assumption that, okay, look at this. Okay, is we want to plot the quantile plot. Okay, as in this case the box and the whisker plot, we can use the basic idea of quantile to plot a compare sample of data. So what is quantile plot? A quantile of sample QF is a value of which specific fraction f of the data less than or equal to f, qf. Okay, so let me see. Quantile plot for paint data. Let me see. Normal quantile plot. Okay, so the normal QQ plot is a plot of YF values ordered observations against Q0 FYF I is I minus 3/8 and plus 1/4. What we need to do is you can use the StatCrunch if I memorize it right. If I remember it's right. If I remember it right, the StatCrunch probably provide the QQ plot. Okay. So basically, you look at the plot and see if it's a normal distribution. Let's look at the example 8.12. Consider data in 10.41, page 351 in chapter 10 in a study. Numerical, we have the data here. Okay. So, what's the question? A question is, the data given in table 1. Construct a normal QQ plot and draw conclusions regarding whether or not it's reasonable to assume that the two samples are from the same distribution. Okay, so normal quantile QQ plot for density data. For that, we can see the station 1 and station 2 the plot. Solutions shows a normal QQ plot for the density measurements. The plot is far from a single straight line. Is not a straight line. In fact, the data from station 1 reflects a few values in the lower tail of the distribution in several up tail. Okay, so you can see the station 1 you have lower and up, right? And the clustering of the observation will make it unlikely that the two samples come from common mu sigma distribution. So when you look at this plot, you can see majority of the station 1 goes way up and it goes way down. Then the other station 2 just goes together at one level and the middle level. So it's unlikely they are coming from the same normal distribution. Okay. Although we have concentrated our development and illustration on probability plotting for the normal distribution, we could focus on any distribution. We would need to compute the quantiles analytically for the theoretical distribution in question. Okay. All right. So that's the whole chapter 8. Okay. Then we're going to look at some homeworks in the next video. Thank you.